Okay, so let's continue to the next step. Okay, the next step is the simplify Navier-Stokes equation using the postulated solution. In this case, okay, this is the we postulated as the this velocity equals to u of the y in the I. Okay, and that's all, right? So the in other words, u equals to uy, v equals to 0, w equals to 0. Okay, so this is the we can take the same thing. Okay, we can do the same thing. Okay, let's start with the just clean up. V and w equals to 0. So this is the this equals to 0. All the terms in the this v equals to 0. All the terms in the w also equals to 0. Since u only depends on the y, so partial derivative with t equal to 0, partial derivative with the x also equals to 0, and then z also equal to 0. And then although this du dy can potentially be non-zero, this b equals to 0, so everything in the left-hand side equal to 0. Okay, this is great. And then we can also, the clean up in the viscous term, which is the this term equals to 0. This equals to 0. Then, the viscous terms only existing for the u. Okay. All right. Then, the same idea, du dx. Okay. If you take a partial derivative, this equals to 0. If you take a partial derivative, this also equals to 0. And then potentially d square u dy equals to non-zero. Okay. Those are the potential terms. Okay. And then what else? Okay. We also need to think about the gravity. Okay. So gravity, in the way we described, is the only in the into the negative y direction. Okay, so this is really telling you gx equals to 0, gz equals to 0, and then gy equals to minus g. Right, so this is great. So let me also clean up. This equals to 0. This equals to 0. This equals to minus g. Okay, so that's pretty much all. I think at this point we didn't make any assumption for the pressure. But let me just clean up here. Okay, so this postulated solution can be simplified as following. In the x direction, okay, in the x direction, this is going to be 0 equals to minus dp dx plus mu times times du u d square u dy square. Okay, and then for the y, this equals to 0 equals to minus rho g minus dp dy, but no viscous term. And then lastly, for the z is going to be minus rho p dp dz. Okay, so these are the three equations. Okay, these are the three equations. Let's call this is the 1, 2, and 3. Okay, and then just like since this is the second time for the create flow, we already did, right? Just like how we did, this is going to first equation is going to give you the velocity field, and then second two equation is going to help to identify pressure field. Okay, so this is great. So let's carry on. The next step here is the let's identify the boundary conditions. Okay. Okay, so this is going to be the boundary condition, but in this case, okay, this is also quite simple. If you okay, we have this from the P, right? Pressure is coming from the left, but however, if we just consider the two boundary conditions, which is the fluid, which is in touch with the wall, then in this case, okay, this is the y, this is the plus h, and then minus h, right? And then okay, this is the 0. So in this case, it's really the at the top at y equals to h top wall, and then the at the y equals to minus h, which is the bottom wall. We are able to find the boundary condition. I mean, both of these are really the no slip, right? So the u equals to 0. This is the no slip. So if we write them explicitly in the equation, then the u y equals to h equals to 0, u u of t y equals to minus h equals to 0. So these are the two boundary conditions which allows you to solve the second order differential equations. Right. So we have all the recipes now. Let's just put it together. Okay. The last step here is the solve the Navier-Stokes equations. Okay. So let's start with the velocity field. Velocity field. So this is not the we can take the first equations. Okay. So equation number 1 is going to give you once again this is 0 equals to this is the minus dp dx plus mu times d square u over dy square. Okay, so this is the we can solve this. Okay, so to solve this, okay, let me make a few comments here. First thing is the pressure gradient. Uh, Okay, we actually said, okay, this is, the pressure changes with x linearly. Okay, dp dx was this nothing but this is, the p2 minus p1 over x2 minus x1 equals to minus delta p over L, if you remember. But this is, the implication of this is this value is the constant. Okay, they changes, they gradually changes, it changes linearly. Okay, so this particular value here is the constant. Okay, so in fact, this is a lot easier. Okay, we just keep this particular expression of the dpdx. However, indeed, it looks like a function, like it's a derivative, right? So it looks like a function, but we can just deal this as the constant. Okay, this is great. That's the first part. The second comment here is we said since u equals to u of the y. Okay, so this is, the partial differential equation that involves this ddy can be considered as the ODE of the dy. Okay, so this is nice. Again, this consideration is necessary to solve the differential equation. Okay, so by putting this together, okay, this equation is going to be nothing but okay. this d square u over dy square. Please note this is ODE. This equals to 1 over mu times 1 over mu times dp dx. Right. So this is the really after we simplify this, in fact, this is nothing but second order ODE. Right, this is something that you are able to solve this, okay? That's something that you are able to solve, right? So let's do this, okay? To solve ODE, we can just keep integrating, okay? So integrate with y, okay? The first integration is going to give you du dy equals to, this is just, please do note, 1 over mu times dp dx is a constant. Okay, so I just write it, it's a bulky, but you can just consider this is d, this doesn't do anything to the function. Okay, this is the y plus a, okay, integrate again. This is the second integration, which gives you u equals to, okay, it's going to be second order in y, so 2 mu dp dx y square plus ay plus b. Okay, so this is great. Find a and b using boundary condition. In this case, boundary condition is the when you plug in the plus y and the minus y, then you know the u equal to 0, right? So this is the we can say at y equals to h, this is u equals to 0, 2 mu dp dx, okay, h square plus h plus b, and then at y equals to minus h, this 0 equals to minus 2 mu dp dx h square, which is coming from the negative h square, minus h plus b. Okay, this is great. And then you know the in fact you know the this is just you know the solving the differential solving the you know the simultaneous equation for a and b, two equation, two unknown. We are able to solve this. Okay, so this is giving this so for the a and b, you can add them up or subtract them each other, and what we can have here is the a is the nothing but 0. This b equals to, it's going to be a sum value, which is corresponding to the minus 2 mu dp dx h square. Okay, so this is great. Just putting all together, overall, what we have here is the u equals to 1 over 2 mu dp dx, and then you can just put them together, which is the this is the y square minus h square. Okay, right. So I will just you know they combine two terms together. So in fact this is the solution, and then if you can take a look, this is in fact the quadratic equations. Okay, so it's a second order quadratic with the y. Okay, so previously this was linear, right? Previously it was linear, but you know the for previously meaning for the crate flow, the velocity profile was turned out to be linear, but in this particular cases, it turned out to be the quadratic. Okay, so let me just do this. Okay, a comment. dE. In fact, let's try to write it. Okay. So what we get here is the one important part is dE. U is dE quadratic with dE. Right? So we call this, the pressure-driven flow. Poiseuille flow is often this is dE parabolic. The parabolic profile. So let me try to describe, what it means. Okay, it's a parabolic profile. Indeed, okay, let's just recall here. This the dp dx. This is the pressure gradient in x is dE delta P over L. This value itself is dE less than 0, okay? So it's going to give you this U equals to minus delta P over 2 mu L, okay? Y square minus H square, okay? So let's try to describe, how this profile look like, okay? So we do have a two walls here, okay? And then let's see. This is dEx. This is the Y. dEh minus H. Right. So indeed, the is something that we sort of know from the beginning. Here is dE for the H and the minus H, right? This is dE no slip. So this is dE. It's that U equals to 0. U equal to 0. For these 2 points, it is no slip, right? So, and then if you plug into the Y equals to 0, okay, for example, okay, just consider Y equals to 0 of dE. Let's try to find the U Y equals to 0. Just plug in the Y equal to 0 here. What you're getting here is dE delta P H square over 2 mu L. Okay, so this is like some, the big positive number, and then you can also see from the symmetry, in fact, this is the highest. This is really the highest. So at this point, there is some flow. Okay, and then this is the EU equals to delta P H square over 2 mu L, and then if this is this looking like a parabolic, okay? This is a quadratic. So this is the velocity profile that we are achieving here, right? And then again, the one last thing is let's always revisit the shear stress. In this case, unlike the case of the equate flow, in fact, there is some variation of the shear stress. So let me try to find out, what it is. Okay. So shear stress is the tau equals to mu times du dy. Okay. So in this case, if you just want to put everything, okay. So this is the mu times. Okay, we can just consider everything into the partial d dy of dEu. And then in this case, U is dE minus delta P over 2 mu L y square minus H square. Okay. So just doing the calculation here, okay? So mu is going to be canceled out, and then what do you have left here is dE, okay, mu times, okay, 2y, okay, so minus delta P 2 mu L times dE to y. All right, so in this case, okay, if we just do calculation, okay, mu is cancelled out, 2 is cancelled. So what we have left here is dE, the minus delta P over L times Y. Okay, so in fact, I'm going to we don't discuss the details, but in fact, this particular equation is there some glitches because we are trying to describe three-dimensional flow into the two-dimension. So we instead of looking at the shear stress, including the sign, we if we want to consider the direction of the shear stress, we have to look at the axial flow. This equation, however, still gives dE magnitude of dE shear stress. So this is, it's shear stress equals to this delta P over L times dE y. Okay, so if you really want to know the maximum and the minimum of the shear stress, okay, so this is going to give you shear stress of the max equals to this is the biggest y. Okay, farthest from the center, then you are getting the maximum. This is going to be delta p times h over l. Okay, so this is dEy equals to plus minus h is going to give you this particular condition. And then this also gives to the minimum shear stress can be found this particular expression, this y equals to 0 at the center line, which is going to be 0. Okay, so the this is also the shear stress. Shear stress is the highest. Okay, let me just put the highest at the wall. And then lowest at the center. Okay, so this really agree with the what we have learned previously, right? This really agrees with the what we have discussed previously. So if I just write this. So so at these 2 points, okay, at these 2 points on the wall, this is this is the gradient of the velocity. Okay, it's actually because of the no slip, it suddenly changed the velocity. So this is the tau max. Tau max is these 2 points, and then if you take a look at this, at point this point is the tau. This is a tau mean, where the two fluid particles are really traveling at the same speed. Okay, so they don't make any difference in the shear stress. Right. So that is all about the velocity here. Okay. So we can also okay. Actually, we can make just a few more comments here. So now we discussed this as the number 3 as a shear stress. So we can take a look at the one additional topics, which is the volumetric flow rate. Okay. Okay, so in this particular flow, okay, so now what we have found here is the volumetric flow rate. So we have some flow rate here. Okay, so in this case, indeed, we are able to consider the flow rate in the plane along the same plane. So if we look at a little bit more carefully, in this case, this particular flow is really in the three-dimensional. So we may consider, this flow is really going into the three dimensions. So if we consider this, the particular location, they do have a same flow profile, right? So if I draw this, okay, this particular direction is the okay. We defined it opposite. This particular direction is the we defined is the z. Okay, so in this case, the something that we can argue is the flow is invariant. Is the flow is the same. We often use the words invariant. It just means it doesn't vary along the z-axis. So what does that mean? What does that mean? We can consider the volumetric flow rate in two ways. Okay, defining the volumetric flow rate is the in 3D. So this is something we have already discussed. Okay, this is the in 3D. We can also consider this. I mean, this is the volumetric flow rate that we have already discussed previously. Okay, so in this case, we use a capital Q, and then this is the L cube divided by T. Okay, and then this is the in fact, this is going to be this some surface integral times this the b b dot dA. Okay, this is dE. This is the volumetric flow rate that we discussed previously, right? So, but now we are able to extend this concept. Okay, we are able to just extend this concept. Okay, this is dE. Because in this particular case, the flow doesn't change along the z direction, we can consider a volumetric flow rate in 2D. Okay, so in this case, if we want to do this, okay, then we are able to consider this lowercase q, which is the instead of the capital Q, we can use the lowercase q. The meaning here is the dimension is defined as the area over time instead of a volume over time. And then the consideration here is if you do here, okay, if we have a U, U is the flow here in this direction. And then if this particular coordinate is the Y, we are able to just integrate the U across the Y. So this is going to give you this u times dy. Okay. So what we are doing this is the essentially this is the same thing. Okay. So this is the volumetric flow rate in the xy plane. So if we I hope this is really the distinguish the two type of volumetric flow. One is the really the flow in the 3D space, or when we have a flow that is the invariant along the z-axis, we can just instead of considering the just the entire 3D space, we can just consider the plane. it's a, so in a sense, it's a planar volumetric flow rate. Okay, so that can be integrated U across the Y. That allows to identify this quantity Q. Okay, so let's try to do apply this in this particular case. Okay, because the flow due to the flow geometry, is the same, which is invariant along the z direction. So let's try to do this. Find the Q for the flow. Okay, so in this case, okay, so in this case, okay, let's say start with the Q is DE. You are going to integrate your linear flow rates across DEY. So this is also, from this particular drawing above, which it probably makes sense, right? So this is going to be, let's just do this, okay? In this case, U is given, okay? U is given as DE minus delta P over 2 mu L y square minus h square. This part is a u, okay? This part is d equals to u. And then we are going to integrate this across the y. So if you remember the coordinate, this particular coordinate we discussed here, this part is d y equals to h. This part is y equals to minus h. So integration goes to from minus h to h, right? So so we can just do this, the quick calculation. So the calculation is just boring, but if you just remember here, we can also do this. Okay, I just introduced this, the integration of the even function. It makes it a bit easier, just because instead of going from the minus h to h, we can just go to from 0 to h. Minus delta p over 2 mu L y square over h square dy. Okay, this part is just a calculation. It is not that important, but in any case, what we have here is dE minus delta p over mu L. And then what we have here is dE, this is dE h cube over 3 minus h square times h. Okay, so this is going to give you the overall. It's going to be 2/3 delta p over mu L h cube. Okay, so this is great. This is we have found. We really found the expression for the q. Okay, so this is going to be the volumetric flow rate. This one is the volumetric flow rate on the xy plane. Okay, so this is great. Please do note the also the although I don't do it here, but you can also check the dimension whether what you get is reasonable, and also make sure after doing the calculation, right? If everything is correct, you should really getting this is a positive number. This is a flow rate, right? So if you calculate it properly, they must have a proper sign as well. Okay, so this is the good way to check your answer. Okay. In any ways, that is the we have made a few additional comments regarding the flow rate of the velocity field, and the velocity field allows us to let us calculate to the volumetric flow rate, etc. Okay, so that is really the end of the flow rate, and then we have one more part. Okay, one more part to calculate is the pressure. Okay, so part B is the pressure field. From the Navier-Stokes equation, Okay, so let me just revisit equation and then 2 and 3 of the Navier-Stokes equation. Okay, so what we had here is the one equation, equation number 2, which is coming from the y equals to minus rho g minus dp dy. And then another equation is the 0 equals to minus dp dz. Okay, so this is really good. Okay, so it's just the note here. How can we simplify this? We can simplify this as following. Originally, this pressure really depends on the four variables. Pressure really depends on the four variables, x, y, z, and t. Okay, so this is really that we are able to make this. There is no t dependence because it's steady. There is no z dependence because of this equation. Okay, this is going to tell you dp dz equals to 0, no z dependence. Okay, so this is going to tell you z. However, for this pressure field, it's a bit more tricky. In fact, we can simplify only this much. Okay, so this is it tells you in fact, the pressure field is the pressure of the x and y. Okay, so they are still having the two variables. Okay, this is especially just recall here. We recall here. This is the dp. Dp dx is the. It actually also depends on the somebody, right? Dp dx is the delta p over L. So dp dx is the non-zero. Okay, this is the non-zero value here, right? So therefore, we still need to keep the p x as one of the variables here. Okay, so so in fact, this makes the calculation slightly more difficult. Okay, so this is going to give you Navier-Stokes equation gives the equation part 2. Uh, Number 2 is giving you dp dy equals to minus rho g. You can make it a gamma, but in fact, this is not the ODE. dp dy is not the ODE. Okay. So we just need to pay some extra thinking here. Okay. We just need to think about just extra thinking. So when you integrate this, um, integrate with the y. What you are what you are getting here is this p equals to minus rho g y plus in fact this must be some function instead of because this is the PDE when you integrate, right, instead of in instead of the the a which is constant. In general, the must add f of the some function with the remaining variables because it's ODE, because it's b, because it is the PDE. Okay. Oh, okay. Right. Okay, yeah, I think there has been some issue at the very end with the syncing, but let me try to get back. Okay, so we are coming back here. Okay, the last part here is the so when you integrate this PDE, because it's not ODE, we have to add the fx instead of the constant. Okay, because it's a PDE. Anyway, if you want to do this, okay, then we can find the let's consider this is the star. Okay, from this equation, okay, differentiate this star with DE with X. Then what we are getting here is DE, this dP dx equals to, the first part is DE really, the 0. So let me just write here, this is DE, this is rho gy plus dx of DE fx, but the first part is equal to 0. So only second part are remaining. Okay. So and then this part is dE, this df dx. Okay. But we know this value is dE equals to minus delta p over L. Okay. This is great. So in fact, this allows us to find out dE. This is dE df of dE dx. Df of dx equals to, in fact, this is dE delta P over L, where this F is dE f of the x, d dx equals to, okay, whether this F has only one variable x, this df dx equals to df dx. Okay, so this is really great. This allows us to find the complete answer. Okay, so this df dx equals to minus delta p over L, and then integrate with dx, right? If you integrate with x, what you have here is def equals to minus delta p over L x plus some constant. Okay, so this is great. Now we know that we found out the complete solution. The overall here, what we have here is dep equals to minus. We are going back to the if we go back to a bit earlier, this pressure is given by de rho gy. Okay, this is going to be rho gy plus fx. So therefore, it must be minus delta p over Lx plus c. Okay. So it's good news. But this is really the how it's depends. Okay. So this is the if we want to analyze here. Okay. Let's just say this particular c is the some constant. Okay, this is just some constant here. Then we are going to have here if we want to analyze here. Okay, what you can say here is the p equals to p of dx y. So if you really want to know how the pressure varies, okay, if you want to know the particular direction here. Okay, so in this case, this is the x, this is the y here. So this is really telling you this first part, right? This is the first part. This part is the number 1. This is the variation of the pressure in the y-axis. Okay, so this is the really the variation of the pressure in the part 1. Okay, so this part is really describing the hydrostatics. Okay. Okay, so that's the part 1, and then this is the part B, which is the x dependence here. This is the this part, right? This is in the part 2. This is the pressure decrease causing the flow. Okay, so this equation really tells you describing the two parts of how the pressure varies within the field. Okay, the distance in the vertical distance, the really is describing the hydrostatic pressure, which is the same as the liquid flow or even hydrostatic we learned in week 2. And also the along the x-axis, we do have the pressure gradient. But this pressure gradient is really causing the flow, which is flowing into the x direction. Okay, so that is the second part. Okay, so overall, right, what we just did here is we have solved Navier-Stokes equation for the Poiseuille flow, which has the two parts. One part is the finding the velocity field, which is causing the parabolic flow. And then in addition, we also identify the pressure field, which has the two components. This is, the y component of the pressure varies due to the hydrostatics, and then x component of the pressure really varies because it is causing the flow. Okay, so that is going to conclude this topic.